Okay. Assalamualaikum warahmatullahi wabarakatuh and a very good morning. My name is Shaza and I am your moderator for today's webinar. On behalf of the Department of Economics, University Technology Mara, Cawangan, Kedah, it is my pleasure to welcome everyone to this webinar. We are honored to be joined by our distinguished guest speaker, Dr. Osaid N.A. Abdul Jawad, Head of Program at Al-Bukhari International University, as well as all respected lecturers and students joining us today. Today's webinar focuses on the topic, a practical guide to using econometrics problem in multiple regression model. For today's session, Dr. Osaid will be presenting on important issues in multiple regression analysis, specifically heteroskedasticity and autocorrelation. Without further delay, it is my pleasure to now invite Dr. Osaid to begin his presentation, starting with heteroskedasticity.
Okay, thank you. Thank you so much, Nurshaza, for your introduction. Assalamu alaikum and very good morning, everyone. I'm very happy and glad to see you today and to meet. We hope that we could make it physical, but it's okay. Let's start with online first, and maybe in the future, inshallah, we can have some physical classes and meetings, inshallah. Thank you so much, Dr. Chua, for inviting me to this session. I hope I will be a good speaker and meet the expectations from the session and make sure that we fulfill the requirements of today's session. Allow me to share my screen. Is that possible? So I can present from my side. Is that okay? I'm just sharing.
Yeah, Mr. Osaid.
Let me know, please, if you can see my slide.
Yes, I can see.
Is it there? Okay, good. Alhamdulillah. Thank you so much. Then okay. First of all, this is me, Said Abdul Jawad, Palestinian lecturer at Al-Bukhari International University, the head of program currently for the Bachelor of Economics. And today, what we are going to discuss is, as the moderator has just explained, that we are going to discuss about the problems in the multiple regressions. This is quite not that advanced discussion, but it is quite far from the introduction in econometrics. Of course, the one who attend these kind of workshops, it's much better if they start with an introduction in the econometrics and some classes in OLS, regression analysis, and also the specification classes in terms of model specifications, in terms of variable selection, and also functional models. Of course, it will be also good if the students knows about the data, types of data, time series data, cross-sectional data, and panel data, the different types of data that we usually use in terms of econometrics. For those students who join this class and this session with good background in econometrics, and they have already attended some classes in econometrics earlier, definitely this session will be very beneficial and will also make it easy for them to follow up. I'm not sure if some of my students who joined from AIU and some other students, if they have not yet attended any econometric class, maybe they will find this discussion quite far from the introduction classes. So, but it's okay. At least you will be aware about what kind of econometrics problem that you may face whenever you run any kind of econometric analysis, especially when we discuss about the most widely used and well-known estimator that we call it ordinary least square, OLS. And whenever we run the OLS, we always, after we run the OLS, we run also the diagnostic tests, which also can help us to detect some kind of problems in the regression analysis. That kind of problems initiated from what we call the classical assumptions of the ordinary least square. This is why I before I start with directly the discussion on the problems, and not exactly as the moderator just said with heteroskedasticity, I may delay the discussion on heteroskedasticity first and start with serial correlation according to the order of the classical assumptions that we maybe you have been introduced before. We have around 7. Before that, I hope my language is clear. I hope my voice is clear. I wish I can speak in Malay and I can explain the things, but I will leave that for Dr. Chua to do it, and maybe other lecturers. If there is any misunderstanding in terms of language and translation, if you need assistance, we will hope that someone will help you with this. But I may continue in Bahasa Inggris. I hope it's okay, guys. And please forgive me for this. So please allow me to just very quick to go through about these 7 classical assumptions. And when we say classical, it is not the classical economics that you hear whenever you attend macro or microeconomics classes, Adam Smith and David Ricardo and other names. These are from classical economics. No, the classical assumptions, these for econometrics and especially for OLS estimators, that we always consider in order to make sure that the OLS is the best estimator for our analysis. Okay. Very quick, of course, number 1 will be the regression model is linear and correctly specified, okay, in terms of functional form and in terms of variables and not omitting any relevant variables or important variables in the models. And whenever we run the analysis and we run the models, econometrics, of course, we need to refer to our economic theories. From there, whatever things the economic theories, basic economic theories says, we need to make sure that we refer to that and specify our models based on the economic theories. Otherwise, definitely we will have problem of misspecification in the econometric models. So that's number 1. Of course, number 2 goes to the error term has a 0 population mean. All explanatory variables are uncorrelated with the error term. Number 4, which is more relevant to what we are going to discuss today, is the observations for the error term. And for what is error term? The error term, of course, for those who doesn't know, the error term that used to be added to any econometrics models that going to explain what other variables that is not included in our model. So whatever variables, whatever effects, whatever explanations about our dependent variable that is not included in our independent variables, the impacts will goes to the error term. Okay, so the observations in the error term is uncorrelated with each other. Okay, that is what we call serial correlation. The good model that has no serial correlation, or other name, we also call it autocorrelation, right? Some people they used to differentiate between serial correlation and autocorrelation in terms of the concepts, okay, in terms of the name, but for simplicity, for now, we just assume that they are the same. And the other one, as we are going to discuss also today, the heteroskedasticity, which is the error term, again, has a constant variance. So whatever we discuss today is the assumptions that is related to the error term in terms of serial correlation and also heteroskedasticity. The other one of the potential problems that also appears in the econometric models, that we call it multicollinearity, right? The multicollinearity, where the explanatory or the independent variables are perfect linear function of each other, meaning there is correlation between the explanatory variables, which I guess I may not have enough time to discuss about multicollinearity today. Okay, I will make sure that I cover the serial correlation and the heteroskedasticity. The assumption number 7 is actually the additional assumptions that is added to our OLS estimator, that where our error terms normally distributed, which is also have a different way to deal with it. I will not go through, I will not cover everything in my slides. I already passed the slides to Dr. Chouad. Maybe she can share it with the students later. And if you just email to me, I will share it with you. But I will not go through one by one. Maybe I will skip for the sake of the time. As we have said that we are going to focus today on classical assumptions number 4 and classical assumptions number 5. Okay, so I will go directly to number 4, yes, where is the observations in the error term is uncorrelated with each other. That is, if a systematic correlation exists between the observations of the error terms, that is where we can say there is an autocorrelation or serial correlation problem, and all estimators is inaccurate. Okay, that is a violation of classical assumptions number 4, especially when we are dealing with a time series models or time series data, because the autocorrelation and serial correlation problems mostly appears in time series data. The other one, that is a classical assumptions number 5, which there is an inconstant variance for the error terms. If the error terms has a constant variance, then we can say that the OLS or the model is homoskedasticity. Okay, at the opposite of heteroskedasticity. If not, and there is a detection of different or non-constant variance among all the error terms in our models, then we can say we also have problem of heteroskedasticity. Each of these problems has way to detect and has ways to test, and also, of course, there is consequences for each term, and for each problem has consequences on our findings or the results of the estimation, either in terms of bias, in terms of coefficients, in terms of standards errors, and but all of them in general makes the OLS unreliable. That is where sometimes we need to use other kind of estimators rather than OLS, as we are going to see today. So here we go. This, yes, one of the problems where we have different variance, okay, over what we call a factor that we call it, usually we call it Z, okay. The more or the higher the Z factor, we can see that the variance of the data is getting changed, where we can see there is inconsistent or non-constant variance. Okay, then I will skip the discussion on classical assumptions number 6, number 7, as we have said that our focus will be only on our classical assumptions number 4 and number 5. So yes, this was called Gauss-Markov theorem and the properties of OLS estimator. Theorem of Gauss-Markov theorem proves that two important properties of the OLS estimates, and it states that the given classical assumptions from number 1 to number 7, okay, the OLS estimator for the coefficients or for betas or for any different number of independent variables that is attached with different coefficients, the minimum variance estimator from among the set of all linear biased estimators with different number of k. The k here, the number of coefficients, okay? It depends on how many variables we have to the addition of that is our constant coefficient. So if all the assumptions from number 1 to number 7, the models or the econometric or OLS meet, and there is no detection of any problem, any econometric, no multicollinearity, no heteroskedasticity, no serial correlation, we can say that the OLS is best linear unbiased estimator. That is, shortly we call it PLUE, blue. Okay, if OLS is blue, means clear, free from any problems, we can say that the OLS is the best estimator of our data. Okay, and there's no need to go for other kind of estimators, GLS or any other kind of econometrics models or any econometrics techniques or econometrics estimators. So yes, this is why OLS is what we call the most convenient, as I can say, the most simple, reliable, and also widely used and widely known among all econometricians who run analysis, that they prefer the OLS estimator, because if it is free from all the problems, we can say that is the best estimator and the best model that we can run. I forgot to mention, please, if anybody has any questions during the discussion, feel free to unmute yourself, speak, ask questions, give your comments. Okay, there's no problem, there's no restrictions. Okay, you can ask, you can stop me anytime, you can say, okay, I cannot understand something, or there's something missing, or please notify me. Anybody, I'm very welcome to any questions during the I don't like to speak alone, please. If I speak alone, especially during online, sometimes feel inconvenient. So please help me with the talking. I don't like to talk alone. So it's good that you also can ask questions during the discussion. Okay, so yes, OLS estimates are unbiased, minimum variance, consistent, normally distributed. If all these things meet at the same times in the same model, we can say yes, OLS or ordinary least square going to be our best estimator because it's blue. Okay, let's start now with the serial correlation. I'm sorry, the moderator, I have to change a bit, so because my preparation starts with the serial correlation, so allow me to start with the serial correlation. That is the most important kind of problems in running econometrics analysis on time series data. Okay, as I know, maybe for the undergraduate level, the most kind of data that we actually use is time series, and even sometimes up to master level where they discuss econometrics, they also run time series analysis. When it goes to other kind of data like cross-section or maybe panel data, that is goes quite advanced, and of course there is another kind of discussions in terms of, because different kind of data we use different kind of econometrics estimators. But let us start with the serial correlation, as it's much more relevant to time series analysis, and then I hope we can have enough time at the end. We can also discuss about the heteroskedasticity. As I said, the violation of classical assumption number 4, okay, that different observations of the error terms are uncorrelated with each other. Serial correlation, that is also called, as I mentioned earlier, autocorrelation or autocorrelation problem. It depends on which book, which econometric books you are referring to. Some books they mention autocorrelation, some books will mention serial correlation. This problem can exist in any research study which order of the observations has more meaning, and of course most frequently in time series data sets, okay, more frequently. It doesn't mean that it does not happen in the cross-section data. There is autocorrelation problems in cross-section data analysis, but the most frequently appears this kind of problems in time series. Why is that? We are going to discuss it. So yeah, in essence, serial correlations implies that the value of the error terms from one time periods depends on some systematic way on the value of the error terms in other time periods, especially when we discuss about the first order serial correlation. When we see that the value of the error terms for the last time period affects and explains the current time unit error term, that is where we can see that the autocorrelation problems might occur. Let us dig deep into the time series. I'm not sure. I hope everyone is aware about the time series data and time series econometrics and the way that we specify our models, whether it is cross-section or time series. If I ask, I hope somebody will respond. Okay, if we look at this first model here about the dependent, the y, the coefficients starting from beta 0, beta 1, beta 2, beta 3, and explanatory variables x1, x2, and x3. From here, can we say something which kind of data we are using in this one, in the first model? Is it time series data or cross-section data? Anybody? I hope so. Anyone, no problem. Is it cross-section or time series, and why? Yeah, it's good to also get response that explains why we are using cross-section or time series. Anyone? No? As already stated here, this is actually cross-sectional, right? Why cross-sectional? Because we use I. Okay, you can see yi, x1i, x2i, and also the epsilon, that is we call the error term. Okay, the epsilon. Some other books maybe they will refer to the error term as e, small e, or small u, or yeah, but this one we use this Greek letter, we call it epsilon I. Okay, so when we use I, that is cross-section. When we say cross-section, that means there is different what we call area, different geographical location, different firm, different country, different banks. It depends what kind of data you are dealing with. But when we go to the time series, we will use T, right? The T here explains that we are dealing with time series data. Okay, YT, X1T, and epsilon T with other also explanatory variables. I hope it's clear. Okay, so when we use time series, we refer to T as for time unit 1, time unit 2, 3, 4. And yes, because sometimes we also use time series data, but it is annual, or sometimes quarterly data, or sometimes semi-annual, or maybe sometimes we use daily data in some cases, because some variables have daily records, okay, like financial data or exchange rate. Sometimes, nowadays, I guess oil prices also have different prices with the conflict happening in the world. So yes, we can also weekly data, monthly data. Yeah, it depends on what kind of variable we are using, but as long as it refers to the time unit, we will use T. The other one that is I have not included, which is we call it panel data, where we use both I and T together in the same model. Okay, but that is out of the scope for today's discussion, so this is why I didn't include in the slides. So yes, time series have different characteristics. The order of the observations in a time series is fixed. time series samples tends to be much smaller than cross-sectional. Yeah, not always, but yeah, in usually the usual practice. There's a the theory underlying time series analysis can be somehow complex because it has some kind of we use time series in order to make some kind of forecasting. We use time series to also run different kind of analysis and different kind of estimators, not only OLS. Okay, the OLS will be the most, as I can say, easy one. Okay, a stochastic error term in the time series is often affected by the events that took place in the previous times, and that is where we are going to face the problem of serial correlation. Okay, and that is why serial correlation problem is usually appears in time series data, because whatever events happens last year, this year we still can see the effects and we still can see the consequences. In any kind of analysis you are studying, like earthquakes. If earthquakes happens last month, this month we still see the consequences and the effects of the earthquakes. Flood, drought, any kind of economic events, recessions, wars, whatever economic events that happens where change, where they do, and there will be a huge impact on the economy that maybe takes time. Okay, it takes time to recover. Of course, the spillover effects will move from one time units to the forward time units, and that is where we see the serial correlation in our data, in the data, and also we see the serial correlation problems in our analysis when we run the time series analysis. Let's differentiate between what we call pure serial correlation. We have pure serial correlation and also impure serial correlation. We are going to see this for both serial correlation and also heteroskedasticity, where we have pure or impure serial correlation or heteroskedasticity. Of course, when classical assumptions is violated, this is pure serial correlation happens, or occurs when the serial correlation happens when the econometric models is correctly specified, meaning that we actually specify our models following the theory, following the theoretical underpinning of the economics, and whatever kind of theories, whether it's classical economics or Keynesian economics or other kind of economics, but we make sure that we actually specify our models and we do not omit any important independent variables in our models. And also the functional form, okay, the functional form, whether the way that we actually write our econometrics model in terms of algebra and in terms of mathematical models, okay, that is also one part of the specifications, and we also take it into consideration and we make sure that it is correctly specified. Okay, and if we correctly specified our model but we still see serial correlation problems that appears in this model, that is what we refer to as pure serial correlation. That is the mostly appears, or the mostly form of pure serial correlation is what we call the first order serial correlation. Why we call the first order serial correlation? Because as we actually going to write here the epsilon t, and to refer back, what we say is that is the error term. Okay, the error term in time t is explained by the error term in the t-1, meaning the time units that happens last time units, whether it is, if you use annual data, then the time units last year. Okay, if you use quarterly data, then the time units last quarter or last month or last week or last day. It depends on what kind of data you are using. Okay, so the error term for the last time units explains and have some effects on the error term in current time unit. Okay, and that is also, there is an error term that is also have other factors that also affects the current error terms, not only the last unit epsilon or the last unit's error term. Then we have to also include the factor, or the what we call the coefficients. If we assume that this is new model, okay, we have coefficients for the last time unit error term that we call it rho. Okay, the name, we call it rho 1. Okay, that is the first order autocorrelation. If this rho, the value is what we call more than 1 or more than 0, so we can see that yes, there is might be problem of autocorrelation. So that is our what we call coefficients, autocorrelation coefficient. We call it first order autocorrelation coefficients, because it is attached and it's multiplied by the error term for the last time unit. So yeah, the size of this coefficients, serial correlation coefficients, that is rho, which indicates the strength of serial correlation. Okay, and yes, if it is 0, if it is the value is 0 multiplied by the epsilon's last time units, then we can say that there is no serial correlation, meaning there is no effects from last time units to today's or current time units of the error term. Okay, if it is the value of rho is 0. But if it is the value approach 1, I mean between -1 and 1, okay, if it is, yes, sometimes there is a positive serial correlation, sometimes there is a negative serial correlation. It depends if the value of rho, whether it is more than 0 or less than 0. Okay, approach 1, the absolute value of the absolute, because this is why we actually take the absolute value of rho. Okay, the high degree of serial correlation exists. Okay, so if it is closer to 1, we can say that, or closer to -1, we can say that the possibility of positive or negative, while actually the negative serial correlation is not really famous, not really applicable. Okay, mostly we face positive serial correlation in our models. But sorry, actually I have to put this in a what we call absolute values. When we say absolute values, so it is not what we call problem whether it is minus or positive, -1, close to -1 or close to +1, it is have the problem. So here we go. We can see if we actually what we call plot the error terms, okay, over time, because we are using time series, right? So over time we can see these the dots that explains the time series and explains the error terms. Okay, so we have something called the positive first order serial correlation, because the current observations of the error term tends to have the same sign. Okay, the same sign of the previous observations in the error term. Okay, if we can see that there is a lot of dots that is following each other in orderly manner in over time, that they follow the same sign of the previous observation, we can see we have positive serial correlation. And this example of negative serial correlation, okay, the example of sorry, again, it's still positive serial correlation, because we still can see whether this one or this one, we still can see that the observations from one time units or to the next time units still have the same value, okay, still have the same sign, not value, sorry, the sign, whether it's negative or positive. So the correlation would be external shocks, so the economy that takes more than one time periods to completely wash through the system. And we can see, yes, the sign, both examples are actually, or both figures are actually an examples of positive serial correlation. And here is where we see what we call negative serial correlation. That is the observations of the error term from one unit to the next one, okay, that they have different signs. So from here to here to here to here to here. So it is some one time is positive, one time is negative. Okay, similarly here from this positive to negative, positive, negative, positive. So we can see that there is different sign for different observations of the error term. That is where we can say we have a negative first order serial correlation. Here is where we can say there is no or the probability of having serial correlation is very low. There is no serial correlation. Why is that? Because in this kind of data or this kind of observations of the error term, it is randomly what we call randomly plotted in the diagram over time. So we cannot see that from the current time units and the next time units whether they are going to follow the same signs or different sign. Yeah, it is unpredictable. And for that one, we can see that there's no serial correlation. Different observations of the error terms are completely uncorrelated, okay, with each other. So the error terms would confirm that that the classical assumptions number 4, which is in terms of serial correlation, is hold. Okay, so we cannot detect any problem of serial correlation. So yes, first way to detect whether we have serial correlation in terms of positive or negative serial correlation, it is possible to identify or detect it by plotting the error terms observations over time, and we can from there maybe we can see. But there is of course other ways that we test for the serial correlation that we are going to discuss now. I hope no questions so far. Okay, I hope it's clear enough. So yeah, serial correlation that can take on many forms. Okay, not only first order. Okay, because sometimes we have seasonal impact, that the impacts of the current problems could remain for the next season, which means quarter or maybe 1, 2 months or 3 months, or so we can see that there is not only one time unit. Okay, that is where we can see more than not only the first order autocorrelation or first order serial correlation in terms of what we call a different observation, and also the impacts will remains for longer time periods, that it's or maybe the impacts of what we call today's error terms has been explained by an event that happens last 3 months if we use monthly data, or maybe the events that happens today that is explained by what happens last 2 years. Okay, that is where we can say the quarterly data. If we use quarterly data, current quarter's error terms may be functionally related with the observations that error in the same quarter but in the previous year. Meaning, if in the last year we can see that there is an event that happens in any of the quarters, especially we call seasonal serial correlation. Okay, seasonal serial correlation, where this year March, February, January, February, March has been explained by the what happens March, January, February, March last year. Okay, this one type of serial correlation. Okay, that is why we sometimes take the time that is t minus 1, which is first order, second order t minus 2, or it depends on what kind of what we call time lag. Okay, we call it time lag. Later on, we also introduce them. That is for pure serial correlation. In terms of impure serial correlation, that happens because of an error in terms of specification of the model. Meaning if our econometric models has been misspecified in terms of independent variables, that there is an important independent variable that has been omitted, or maybe there is one irrelevant independent variable that has been added to the model, that is also possibility that happens, that will also create a problem of serial correlation. But this is kind of serial correlation that we call it impure serial correlation. So yes, either because usually, the most cases, that is because of omitted variable or incorrect functional form of our models. So yeah, suppose that the true equation, this is our true equation, and now because we accidentally dropped or omitted the x2, which we actually consider this variable as one of the important variables to be included in our models, then yes, we will see that the impacts, okay, the effects of the second explanatory variables on the dependent variable is now included in our error term. That's why we call it epsilon t star. Okay, because now the epsilon t star is also included the x2. Why? Because it's already been omitted or dropped from our first model. Okay, so this epsilon star tends to exhibit detectable serial correlation. X2 itself is serially correlated, okay, in its own, and the size of the epsilon is small compared to the size of the estimated, or we call beta 2, and also the estimated x2, okay, that is multiplied by the coefficients beta 2, in terms of the size, and also in terms of the if it is by its own serially correlated, then definitely we will see that our what we call epsilon, our error term, is serially correlated, and we will detect the problem of serial correlation. Okay, yeah. So now, whenever we actually run the regressions, suppose this our initial equation, because this impure serial correlation, when it happens with the what we call squared, okay, x2. So the new error terms here, which is also, if it is also being omitted, okay, where we see that again the error terms is changed, because now it also includes the impacts or the effects of the second explanatory variables that was omitted. Whether it is polynomial, linear, or non-linear, we'll still see the problem of autoregressive pattern. So here we go, incorrect functional form. That is for omitting variable, and incorrect functional form if it is accidentally being misspecified, okay, in terms of omitted variable and in terms of functional form. So we can see incorrect functional form as a source of impure serial correlation. That is our new what we call regression line, okay, the new regression line that follows. And here is our observations for the error term, that we clearly can see that the serial correlation exists, because yes, we can see that they and yes, this is what we call again positive serial correlation. Why? Because most of the observations are following the same sign of the previous observations of the error term. Okay. Consequences. Yes, when we discuss, it's also important to see what is the consequences of the error terms and the consequences of problems in the error term, especially when it is in terms of serial correlation or heteroskedasticity. For pure serial correlation does not cause bias in terms of coefficients. Okay, the coefficients will not be biased. Okay, but the serial correlation causes the OLS to be no longer the minimum variance. Means all linear estimators, meaning OLS is not reliable. OLS is not what we call the results of OLS will not really explains, and the estimation results does not actually, even though the explanatory variables and the data is good and the results is significance and the p-value r squared is good, but when it comes to pure serial correlation, is correctly specified model, but the serial correlation still exists, the OLS is not minimum variance estimator, meaning it's not blue. Okay, we cannot use it as the best. We need to see how we can what we call use any other kind of estimators. It also causes the OLS estimates of the standard errors. Okay, the standard errors, the serial correlation cause the standard errors to be biased. Okay, and when we say biased, is the estimated value is not or I mean very far from the actual value. That is what we call biased. When we see that there is the estimation value is not the same as the actual value, this is what we call the biased, where we can see that the estimation is not really represents the actual value of the parameters. Okay, whenever we discuss about for those who have good foundation in statistics, whenever there is biased, we can say that the values are skewed or the values are not following the same, or the estimations is not having the same actual value of the parameters. That's why we can see the residuals. Okay, the residuals, and the residuals is quite high. Detection, how we can detect? Yes, just now we see how we can detect the serial correlation problems in terms of data, and we plot the data, and from there we can see that we can see if there is any serial correlation problems. But softwares that is available right now, econometric softwares that we actually use in statistics and in econometrics, such as eViews, Data, maybe some other people use RStudio or other kind of statistical softwares, do provide us with some tests, okay, that help us to detect the problem of either serial correlation or heteroskedasticity. The first one is Darwin-Watson test and Lagrange multiplier test. Both tests have different way to find it. I think I will not have time to discuss about the Lagrange multiplier. Maybe I will discuss only about the Darwin-Watson. I hope that it is good because it's widely known and also very reliable one. Even though sometimes the Lagrange is also much widely used, that is going to see why. Darwin-Watson test that is used to determine if there is a first order serial correlation. Okay, the first order serial correlation deductor. We can use this test in order to see whether we have first order serial correlation in our model or not. And requires these three assumptions. The model is regression model includes intercept terms, should have intercepts. Serial correlation is first order in nature. Okay, the first order in nature serial correlation problem do exist in our models. And the regression model does not include a lagged dependent variable as the independent variables. Okay, the regression model does not include any lagged dependent as how the independent variable lagged. I'm not going to explain how we actually calculate the value of D. That's our Darwin-Watson value. Okay, that the statistics, the test statistics that we use to calculate our Darwin-Watson. Because actually nowadays we never use it manually. Okay, we use the software that is easy for us to calculate. Maybe later, if we have some hands-on and we have some time, I will show you how we can do it on maybe on Stata. Okay, I'm not sure if you are familiar with Stata or maybe with eViews, but it's possible to use anyone. eViews is also good. Actually, for eViews, whenever you run the regression, the results of the Darwin-Watson will be automatically there. Okay, if we have time, inshallah, I will try to show you how we can do that. So yeah, this is actually the test statistics that we use to calculate the D value for the Darwin-Watson. And the D value, it is actually, yes, if it is extreme positive serial correlation, if D is equal to 0, extreme positive negative, negative serial correlation, if it is closer to 4, okay, it's close to 4. So and if it is close to 2, we can see there is no serial correlation. So in terms of the value, it is from 0 to 4. Okay, the value of D from 0 to 4. If it is close to 0, positive serial correlation, close to 4 is negative serial correlation, and if it is close to 2, there is no serial correlation. But again, that one requires to test the hypothesis for the D statistics, okay, for the Darwin-Watson statistics. That will be unusual for the two respects. If econometricians almost never test one-sided null hypothesis, okay, so Darwin-Watson is two-side test. That is, there is a negative serial correlation. Darwin-Watson test has acceptance region. Okay, there is an acceptance region where later we can show where's the acceptance region and the rejection region. And the weakness of the Darwin-Watson test, it is that they have inconclusive region. Okay, there is an inconclusive region that we cannot say whether it is reject or cannot reject the null hypothesis. Okay, with these exceptions, Darwin-Watson test is quite similar to the test statistics or the T statistics. Okay, the T statistics. So here we go. This is how we actually develop our hypothesis to detect whether we have no positive serial correlation or there is a positive serial correlation. Okay, we obtain the residuals. Okay, first of all, the steps we test the positive serial correlation. We obtain the OLS residuals from the equation. Okay, and calculate the D value, determines the sample size because we also need to see how many observations we have, right? And then we also see from the table, we have what we call Darwin-Watson test table. Maybe later I also can show the Darwin-Watson test table that show the DU, the upper value of the D and the lower DL. Okay, DU and DL. And to see where is the rejection region and where is the not to reject region and the inconclusive region. But this is actually how we build our typical Darwin-Watson test hypothesis. And from there, we run the analysis and we check the value of the T for the D, okay, the Darwin-Watson value, and then we can see where is our lower and upper region. And from there, we will also see if the D value is less than the lower D, we reject the null hypothesis. And if we reject the null hypothesis, we will confirm that there is a positive serial correlation in our model. If the D from the test statistics is more than the upper value from the table of the D, we will not reject. And if we do not reject the null hypothesis, we will say and conclude that there is no positive serial correlation in our model. But if it happens that the D value is in between the lower and the upper value of D from the table, we say that is inconclusive. Okay, and from there we will maybe need to run the Lagrange multiplier test in order to check for the what we call the serial correlation. This is an example that, yes, here we go. And once we calculate and we run the analysis and we do the estimations, we build the hypothesis, we get this from the table. Okay, the DL, the DU, and the number of observation is 25. We have 3 independent variables. This is our K. Okay, the number of K, because whenever we go and check, let me just show you the table. Okay, I will just show you the table, the nature of how the table looks like. I hope you still can see my screen. Yeah, these are the tables, and let me just go, I think P4. Yeah, here we go. These are the critical values for the Darwin-Watson test for the DL and the DU, depending on how many independent variables we have, the number of K, how many independent variables we have. Okay, for each independent variables and the number of observation N. How much the number of observation and how many K, we will get 2 values. One for the DL, lower value for the Darwin-Watson, and the upper. Okay, it depending on how many N or number of observations we have. Back to here. So we can see, yes, from this example, very simple example, at 5% statistics, we test, okay, at 5%, what we call significant value. We have 25N, we have 3 variables. Then from the table, we get the lower and the upper, okay, and we develop our what we call hypothesis for the serial correlation. And these are the decision rules, whether we reject or not to reject, and where is the inconclusive region. Now we have different values for the statistics, the test statistics, that is D, okay, and we got these values from the formula here. This formula will help us to calculate the value of D. Okay, in different value, we can see that the D could occur and lies on different regions. We have the rejection region. If the D is 60% here, okay, if the D is 60%, we will reject the null hypothesis and conclude that we have a serial correlation problem. Why? Because the D value from the test statistics is less than the lower value from the table. If it is above, okay, if it is above the DU, is our DU 1.66, we can say that the null hypothesis is not rejected, and we conclude that there is no positive serial correlation. And here is in between, in case we have the D value is between the upper, the lower, between the lower and the upper value of the D from the table, we can say that the inconclusive region. Okay, inconclusive region. I will skip the examples because maybe I will do some hands-on session later on. But you will see the same. Okay, you will see the same. I think okay, it's too late already. There is another test. Okay, just to make it very quick, that we call it Lagrange multiplier, or LM test, that we also use to detect for the serial correlation problems, or for the autocorrelation, using this what we call Godfrey test. Okay, Godfrey test that we actually generates our residuals. I hope you know how to actually calculate the residuals, because that is very important. that the actual y minus the estimated value of y. Okay, these are the residuals. And we have to create what we call auxiliary equation that going to help us to run what we call the Proust-Godfrey test that we actually use in our softwares. We will use the terms of auxiliary equation more when we discuss about heteroskedasticity, okay? Because there's also two tests to detect for heteroskedasticity that we actually need to run auxiliary equation. So yes, for the LM test statistics is N, which is actually the number of observations multiplied by the unadjusted, okay, the R squared, unadjusted R squared that we actually get whenever we run any regression analysis. Again, you don't have to trouble yourself. Sometimes you may be asked to calculate the R squared, because yes, we can actually find the R squared from what we call the ANOVA table, I guess, as we are going to calculate the random total statistics and estimated and also the actual. But yes, softwares is there to also help us whenever we run any regressions, the R squared value will be available. Okay, that if you are not using manual calculation. Okay, again, we have also the value, okay, the value for the test statistics, and that will be compared with the degrees of freedom, how many degrees of freedom, and at 5%, we also have the critical value from the table, and from there we can actually run the hypothesis. We can test the hypothesis, whether to reject or not to reject. We can check for the serial correlation using the Lagrange multiplier, but I'm really sorry because I don't have enough time to go in details to explain about it. The last part will be how we can actually correct if we run the Darwin-Watson, or if we run the Lagrange multiplier test and we detect that there is a problem of serial correlation. We have some ways to what we call correct. Okay, we call it remedies for the serial correlation problems. Okay, again, to run these remedies, we can use what we call general least square, which is actually different from OLS. Yes, because if it is serial correlation in correctly specified model, and we still see the serial correlation problem do exists in the model, we will not use OLS, because OLS results is unreliable, okay, because it's not blue and is no longer what we call accept the results from OLS. This is why we actually tend to run generalized least squares, or what we call Newey-West standards error. Okay, Newey-West standards error, that by running this kind of estimators, we can say that our serial correlation problems somehow disappear from the models. Again, maybe not have enough time to go through both of them. Let me just focus on generalize these squares, okay? That reads an equation of pure first order serial correlation, okay? And restores the minimum variance property to the estimation for the error terms. GLS starts with an equation that has pure serial correlation and transform this model into that does not have pure serial correlation. And it's instructive to examine this transformation in order to understand the generalized least square, where we can see that one model here that expected or assumed that it has serial correlation, and we are going to substitute, okay, the value of epsilon, that is explained by the previous or last time units. In terms of annual, we say last year value of observations of the error term that is multiplied by the rho. If you still remember, that is our serial correlation coefficients, and we substitute it in our original model. Okay, so the whole values here plus the error terms of the error term. Okay, that is substituted in the error term in the epsilons. Okay, here, and then we multiply this equation by both sides. Okay, both sides of this equation we multiply by the rho, which is the coefficients, serial correlation coefficients, and also the lag. Okay, the lag error term. Okay, but we also take the lag for the independent variables. Okay, 1 minus t minus 1, and also the t minus 1 for the dependent variable. Okay, if we subtract these two equations from each other, this one and this one, we are going to get this equation that we actually change the name. Okay, we substitute in terms of saying yt minus rho, yt minus 1, we just say y star. So the y star will equals to beta star, that is the beta 0 multiplied by 1 minus rho. Okay, why is that? Because we actually subtracted these equations from the old equation after we multiply it by the coefficients and the lag, 1 period lag. Okay, because we are dealing with the first order serial correlation. Okay, then we get new model, new formula that we assume it is what we call free from serial correlation problem. Okay, as we are going to estimate this new data. Okay, so yes, each part of this new formula is explained here. Okay, so the error term is not serially correlated anymore. The slope coefficients rho is the same as the slope of coefficients. Why is that? Again, because when we discuss this, we say that our serial correlation does not, or the consequences of serial correlation does not affect the coefficients. Okay, it affects only the standard errors and making the standard errors biased. Okay, but it does not make the coefficients biased. This is why the slope of the coefficients remains the same. The coefficients for the rho is the same slope coefficients for the original equation. The dependent variable has changed, which means the GLS generalized least square adjusted R square is not comparable to the OLS adjusted R square. R square. This is why we cannot use adjusted R squares to see how much the model fit. So OLS cannot estimate generalized least square model. Okay, and the techniques that we actually run on the software is that we use Paris-Winston method. Okay, Paris-Winston method. Maybe we are actually going to see that after a while. So yeah, we estimate rho by running the regression based on the residuals, and then we add these estimated coefficients for the serial correlation to estimate the generalized equation with the OLS with the adjusted data. Okay, after we adjust the data, and these steps represent repeated until the further improvements result. Is the final estimate. This is one of the examples that we can actually see the difference and run both OLS and GLS, and these are the results after the estimation. Okay, these are the results after the estimations regarding how much the coefficient size, the coefficient sign, the standard error that is in between the brackets, the test statistics, the t-test statistics for each variable, and also the adjusted R-squares, the number of observation, and whenever we run the GLS, we also can get this data as well. Okay, I think I'll skip the New West because this is another let's say way to correct the serial correlation problems in our model. So yeah, before we start with the heteroskedasticity, is there any problem? Is there any question? Would you allow me to do some kind of hands-on? Is it possible? And then we can take a break. Is it possible, Doctor? I think we need a break. Maybe
Yes,
this will
yes.
quite heavy discussion, I believe. Before we go for break, just allow me just to go very quick to open my data. Okay.
Sure, you can.
Allow me just to, I'm not sure if you're familiar with the interface of this data. This is our data software. Okay. Allow me just to import one Excel sheet that I have prepared earlier for this hands-on session. And I keep it, I guess, yeah, here. So here, this data that we have, okay, I will make sure that our first row is for actually the name for our variables. And the model that I'm going to run is the consumption function. I hope that everybody is aware what is consumption function, what is the variables that we use in order to test the consumption function. And we can see that these are actually annual data, time series annual data. These are the data from, yeah, 1945 to 19, no, I think it is more than this. Let me just open it. Okay, I will click OK, I will open the data here. You can see these are the data from, yeah, 1945 to 2006 is annual data that has values of consumption, households consumption. These are our dependent variable, and the independent variable is the of course the disposable income. Okay, the disposable income and the interest rates. This might be the major two independent variables that explains the consumption, households consumption. Okay, so I will run the analysis using Stata. I will follow the commands. I also have prepared the commands that we actually use in order to run the analysis. First of all, we have to make sure that the Stata knows what kind of data we are dealing with. I will just tell the Stata that we are dealing with time series data. So I will write the commands ts set year. So the Stata will be aware that I'm actually using time series data, annual time series data. So year is our time unit, annual from 1945 to 2006 data. Then I will go to run the analysis. I will just run, will write the data, the ask data to run me the analysis of regression analysis, the simple regression, OLS. Okay, I will write regress, and I will write first my dependent variable, which is the personal consumption, and next will be the two main independent variables, that is disposable income and the interest rates. So here we go. After I click enter, we are generating the results. This is our results. These are the number of observation. You can see here, you can see the R squared, the adjusted R squared, and from here you can see the coefficients for the variables for disposable income and also for the interest rates. And we can see that the both variables are actually significant at 0.0 0.01, or we other ways we call it 1%. Okay, significant at 1%. So this is the data. This is the normal data or findings that we actually, or results from the OLS regression analysis. Next, I will check whether we have a serial correlation or there is no serial correlation in our model. So I will run the Darwin-Watson. So instead of manually calculating the D value, I will ask Stata to actually run and find me the D value. Okay, then we will compare that D value with the critical values from the table, the Darwin-Watson table, especially when we get the what we call the upper and the lower values. So let's start with the ESTAT comments, DWATSON, and we click enter. Here we go. This is our D value. In eViews, if you are familiar more with eViews, eViews will actually provide the Darwin-Watson value together with the regression. Whenever you use eViews, you run your analysis using eViews, the results of the regression will also include the Darwin-Watson statistics. So here we go. This is our statistics, test statistics for the values of the Darwin-Watson. We have how many? K? We have 3, right? Because we have 3 variables. K, 3, how many number of observation? 62. If we go to the table and we have K equals to 3, right? Here we go. K equal to 3. And we go down and we try to see the number of observations, 62, we don't have. The nearest one might be the 65. So maybe we can take these 65 values, okay? The number of K, we have, two independent variables. Okay, so the number of K here equal is 2. So 65, we take these 2 values. This is the lower values and this is the upper values. So from here, from these results, what you can see, guys, is it is lower than or upper or more than the critical values. I'm here back. I hope you can see. I'm not sure if the values are okay. Okay, I'm zooming in, so it might be much clearer. So we have, this is the lower, this is the upper. Okay, the values of the Darwin-Watson test is this much. It's clearly the value of D from the test statistics is less than 1.54. So it is less than the lower value. Okay, less than the lower value. So if it is less than the lower value, we are, here's the lower value, we are in the rejection region, right? It is rejection region. If it is rejection region, we reject the null hypothesis. What is the null hypothesis? That is, again, back to our null hypothesis for the Darwin-Watson. Here we go. The null hypothesis, no positive serial correlation. If we reject this null hypothesis, then our alternative hypothesis is true, and we can say and conclude that positive serial correlation do exist in our model. Okay, so we can say that these results, even though the R-square is good, the coefficient size is good, as correctly specified, and all okay, all are significant, right? But because the model has actually serial correlation problem, we have to run some kind of remedies to get rid from the serial correlation. We also can run Lagrange multiplier. That's also another way to find to conclude that there is serial correlation, but I will skip that. I will go to run the generalized least square. That will I again run the regression analysis of the OLS, and from there I will what we call use the what we call Paris command. Okay, back to here. Generalized least square, we use Paris-Winston methods. Okay, where Paris-Winston methods, where actually this generalized least square estimation is expected that it has no problem of serial correlation. Then I will run the Paris command for, again, the same variables, same dependent and same independent variables, and I click enter, and here we go. That is our results for the Paris, and we can see that the Darwin-Watson statistics of the original and the transformed one is now 2.18, right? 2.18, which is what we call conclude that this generalized least square model do fit better than the OLS, and we consider the results of the GLS instead of the results for OLS. So yes, these are all the values for the coefficients, for the statistics, and also for the R squared. And again, because the adjusted R squared is what we call unreliable to be used to compare between the how much fit the OLS and the GLS. Okay, these are the number of how the number of what we call how many times we find the coefficients. Okay, the serial correlation coefficients has been changed. Okay, for each time the row value has changed. So yes, then the final estimation, the value of rho was this much, where we can see the serial correlation problems has been what we call removed. Okay, in somehow we can say removed from the analysis. I hope it is clear enough, and I follow the steps as in my slides. As I said, we also can use what we call the Newey-West standard errors. That is another way to get rid of the serial correlation problems in our models. But because of the time, I will skip, and later, after a few minutes, we will discuss about the heteroskedasticity. Can we have a break of few minutes? Is it possible?
Thank you, Dr. Said, for the clear and insightful presentation. Before we break, we shall now proceed to the Q&A session first. So if there are any questions, participants may either unmute and ask directly or type the questions in the chat box. Thank you. Okay, so if there is no questions, then we'll now take a 5-minute break before proceeding to the second session. Thank you.
Okay. Are we okay to resume our discussion? I'm okay.
Yes. So thank you, Dr. Said. So we shall now proceed with the second session. So in this
Okay.
session, Dr. Said will discuss about heteroskedasticity. So without further delay, I would like to invite Dr. Said to continue his presentation. Thank you.
Okay. Thank you so much, and welcome again for to continue our discussion today for the another potential problems that we usually face whenever we run our regression models, that is heteroskedasticity, which is quite somehow related to serial correlation, because we still remain at the issues, econometric problems that is related to error term. Okay, the error term problems that we actually face, it is serial correlation, that is have the explained by the previous time units. But when it comes to heteroskedasticity, as same we discussed in serial correlation, we have pure and impure. Let's start with the pure heteroskedasticity, that is referred to the heteroskedasticity problems that when occur in a correctly specified equation or correctly specified model. Okay, there is no relevance or important variable being omitted, or there is no irrelevant variable being added, or there is no incorrect functional form for the models, and we run the analysis and we still detect problem of serial heteroskedasticity in the error terms, and we see that the error terms is what we call not constant. Okay, that is a violation of the classical assumptions number 5. Okay, that is assumed that the econometric models are homoscedastic. Okay, but unfortunately, sometimes we will have problem that the constants for the error terms, the variance. Okay, the variance is not constant. The error term variance is not constant. Okay, so that is where they see the variance. Okay, VER variance for the error terms is or the sigma square, because sigma square, right? D is constant. That is where we can see that the model is homoscedastic. And the violation of these assumptions, where the variance or the sigma squares is not constant, means the variance is not constant for the error terms. That is the problem of heteroscedastic appears in our model. And through the experience, this kind of statistics or econometrics problems appears mostly in cross-sectional data. Yeah, cross-sectional data. But it does not mean that it does not happen in time series. It's also possible that we can, or we run time series analysis or time series econometrics, and we still face the problem of heteroskedasticity. Okay, yeah, it often occurs in data set in which there are large disparity between the largest and the smallest observed values of the dependent variable. The simplest way to visualize pure heteroskedasticity is to picture the observations of the error terms and group them into distribution like wide or narrow. Both groups can be centered on 0, but has larger variance. Okay, you can see that homoscedastic is where what the variance is constant, but in heteroskedastic you can see that there is sometimes is large, sometimes what we call wide. Okay, wide dispersion or distribution of the error term, or sometimes it's narrow. Okay, that is what we call inconsistent variance in the error terms, where we can see that there is a pure heteroskedastic problems. Okay, so this is homoskedasticity, and this is discrete heteroskedasticity. That's sometimes narrow, sometimes wider. Homoskedasticity is the distribution of the error terms has a constant variance. Okay, constant variance. So the observations are continually drawn from the same distribution. And the simplest heteroskedastic case, that is discrete heteroskedastic, with we have two different error terms variance. Okay, one is wide, one is narrow. Okay, which could be drawn. So yeah, heteroskedasticity can take on many complex forms. Okay, one model has the variance of the error term related to an exogenous variable. Okay, exogenous variable that we call it Z. Okay, and the difference here is that we use I instead of T. Why? Because we use what we call cross-sectional data, not time series data, as we said, cross-sectional data, where we actually the potential of having or facing problems of heteroskedasticity more in cross-section data. So these exogenous variables that is added and that could cause changes, and it will be multiplied by the variance. We also call it proportionality factor. Okay, proportionality factor. That the value of this proportionality factor is going to help us to deduct whether we have heteroskedasticity that will be multiplied by the variance for the error terms. Okay, sigma square, and that will determines whether we face this or not. Exactly how we discuss the factor rho in serial correlation. Okay, so here we go. If we plot these data and we use the value of this proportionality factor that we call it Z, we can see that yes, this is probability distribution for the 0, less than 0, more than 0, here's 0, and along this factor, proportionality factor that we call it Z, that is exogenous factor, the higher the value of Z, we still can see the variance is normally distributed and consistent. Okay, meaning no matter how much the value of Z change, we still can find that the variance of the error terms, okay, consistent. That is where we see that there is homoskedasticity. Okay, the error term here is homoskedastic with the respect of the value of Z. So the variance of the distributions of the error terms is constant, meaning is the same. So no matter how much the value of Z, in this case, there's no change in the variance. We still can find that the classical assumptions number 5 hold. Okay, and there is no problem of heteroskedasticity in the model. If we have this case where along the exogenous variable that we call it Z, okay, the higher the value of Z, we can see that the variance, okay, the variance of our error terms is changing. It was narrow here, wider here, and more wider here. So there is inconsistent variance. Okay, the variance will change for the error terms. The higher the value of these exogenous variables or proportionality factor Z is increased, we can see that the variance change or become wider for our error terms. Here is what we call heteroskedastic error terms. Okay, the error terms is heteroskedastic. The variance of the distribution of the error terms changes systematically as the functions of Z in this example. So we can see that the factor Z has an effect of the variance, and the classical assumptions number 5 for the OLS is violated. Okay, and there is a problem of heteroskedasticity in our model. It can occur in time series, as I said, with significant amount of change in the dependent variable. It can also occur in any model, cross-section or time series, where the quality of the data collection changes dramatically, of course. As a measurement error decrease in the size, so should the variance of the error term also decrease. Heteroskedasticity caused by an error in specification, we call it impure heteroskedasticity. Okay, the heteroskedasticity that happens with correctly specified model, it is pure. The impure heteroskedasticity that we refer to problem of heteroskedasticity, that if it happens because we misspecify our models, means our model have problem of misspecification, either by the selection of the independent variables or by the selection of functional form. Okay, 3 major consequences of heteroskedasticity. We see pure heteroskedasticity, again, not cause bias in the coefficients estimates. Okay, heteroskedasticity typically causes OLS no longer to be minimum variance estimator, meaning not blue anymore. Okay, it's not blue, and the results is irrelevance. OLS is unreliable estimator. So all these linear unbiased estimator. Heteroskedasticity causes the OLS estimates of the error terms to be biased, exactly as serial correlation, and leading to unreliable hypothesis testing and also confidence intervals. This is why whenever we run the hypothesis testing for the OLS with the existence of heteroskedasticity, the results is not reliable and we cannot make any assumptions or any conclusion or any policy recommendations, because if we are running data, economic data, we are dealing with economic data, because yes, finance students, they also use econometrics, but for economics, I'm not sure if all of our students attending is economic students. Whenever we run our analysis, of course, we need to make some kind of policy recommendations, right? To policymakers, to CEOs, to firms, what we call policymakers, banks, policymakers, central banks, sometimes policymakers. It depends what kind of data and what kinds of model we are running. But as long as we are using OLS, and the OLS results is one of the important classical assumptions of the OLS is violated, we cannot rely on the results of OLS to make conclusion about our data and to make some policy recommendations about our data, unless we use different estimators or we use the remedies. Okay, we get rid of the problems of serial correlation and heteroskedasticity and also multicollinearity that we have not discussed in today's session. Now, to test for the heteroskedasticity, again, we have two. We have two heteroskedasticity tests that allows us to test whether the heteroskedasticity problems occur in our models or not. First one is what we call Prosh-Pagan test. Okay, Prosh-Pagan test, and the second one is we called Y test. Okay, both of these tests, of course, as we discussed in the Lagrange models for the serial correlation, we need to get help of the auxiliary equation that allows us to help us to run the analysis where we can deduct the heteroskedasticity problems exists or not. Okay, and before we test for the heteroskedasticity, we start asking if are there any obvious specification errors in terms of missing or omitting variables, important variables in our models, or misspecified in terms of functional form, whether it's binomial, not binomial, and any other kind of functional form, because sometimes in our functional form is play a major role, the way that we specify our model mathematical and algebra way. Are there any early warnings of signs of heteroskedasticity? I mean, if we plot the data and we get the residual, we plot the residuals, we get the variance for different factor, different maybe time zone, if we use time series, if we use cross section, maybe with different, especially if we run analysis on cross section for different states. For example, some states are big states, some states are small. If we run analysis on Malaysia, right, and we run analysis, cross-sectional analysis from, and we acquire the data from different states. Of course, the state of Selangor, the state of Pahang, the state of Kelantan, Johor, maybe these are big states compared to maybe Perlis or Penang or Malacca. That is where the maybe in terms of population, the number of population, the size. So yeah, we can see that there is different variance. It's expected. Okay, there is an early signs that the heteroskedasticity problems appears in our model. Okay, but even before we run any of these heteroskedasticity tests. The other one, does the graph of the residuals show any evidence? Exactly the same as we done here. If we graph our error terms and we see that with different occasion, with different cross-section analysis, or if we run time series with different time, we can see there is a factor that that makes the variance to be changed or to be not constant. Yes, that is where we can have an early signs and see there's a potential of heteroskedasticity in our model. So yeah, for example, this eyeballing residuals for possible heteroskedasticity, where we can see here clearly that the error terms, yeah, these are error terms. After we plot the observations of the error term, that see that there is inconstant or not constant variance. Okay, that where small is associated with small z's in terms of proportionality factor, or large is associated with a large z. And similar here, we'll start with a large and it becomes small. It depends on the proportionality factor, that is, we call it z. The higher, okay, the higher the z, we can see that the dispersion is different, means the variance is getting difference. That is where we can expect or guess that heteroskedasticity problems appears in our model. Here is that we have where, yes, all the way, the higher the z, we can see that the starts with small, then yeah, large, and then small again. Okay, if you plot the residual of an equation with respect to potential z proportionality factor, a pattern in the residuals is in indication of possible heteroskedasticity. Okay, allow us to start with the first way, okay, first detector, okay, that we call it Prospegen test, that helps us to test whether the heteroskedasticity problems appears or not. Okay, that will investigate whether the squared residuals, okay, the squared residuals can be explained by the possible proportionality factor. Okay, there's 3 steps. First of all, we obtain the residuals. How we obtain the residuals? We subtract the estimated values of y from the actual value of y. Okay, so we obtain the residuals from the estimated equation for an equation with 2 independent variables. Okay, there is 2 independent variables, and again, as you can see from this equation, we use I instead of T. That means we run data that is what we call cross-section. Okay, cross-section data. Then what we do, the second step, we square the residuals as a dependent variable on this, what we call auxiliary equation. Okay, auxiliary equation. After we get this equation, of course, we will substitute the two independent variables after the estimation in our error in our residuals. Okay, yi remains the same minus all these factors are actually a part of the estimated yi. This is why we use hat, right? If you remember, for those who have experience and attended early classes in econometrics, the difference between actual y and the estimated y that we put hat at the top of the variable. Okay, the hat here means that this variable or these are the estimated values. Okay, the estimated values, not the actual values. To see the residuals, we subtract the estimated from the actual one, and we get our residuals, auxiliary equation. And we, in order not to confuse, okay, between the original estimation coefficients and these auxiliary equation, we just change the name of the parameters. Okay, instead of use beta, maybe we can use theta, we can use gamma, we can use alpha. So this is alpha. Okay, in this example, we use alpha. I don't know if you refer to other book, maybe you will use other kind of coefficients. Okay, it's okay. There's no problem. Still can be, but because not to confuse with these betas, that is our coefficients from the original equation. Okay, and this is for auxiliary equation. We change the coefficients so we don't confuse. Then the step number 3, yes, and then we square. Okay, we square the error terms, the residuals. Sorry. Yes, the test of overall significance of the chi-square. Okay, then we can expect what kind of statistics we are going to use is the chi-square test. I hope you are familiar with the chi-square. If you have attended any applied statistics course, the time when you test the hypothesis for the variance, we use chi-square test statistics. What is the hypothesis? How we develop the hypothesis? As long as we have two independent variables, we have coefficients that are equals to 0. That is what our null hypothesis. Our alternative hypothesis is that this null hypothesis is false. Okay, then we can deduct whether the heteroskedasticity appears or not. So we use n multiplies by the r squared. Okay, whenever we run the analysis, this is our number of observations. This is our r squared value. We multiply and we get the degrees of freedom that equal the degrees of freedom here that equals to the number of slopes coefficients in the auxiliary equation. Okay, in the auxiliary equation. How many in the auxiliary equation? We have coefficients. Okay, the coefficients of slope coefficients, not the constant. We exclude the constant. So in this case, because we have only two coefficients for two independent variables, then our degrees of freedom is equals to 2. Okay. If we have 3 independent variables, we add one more. Then it is 3 degrees of freedom. But because in this case we have 2, then degrees of freedom is 2. Look at this example. This is one of the examples. Also can be see. This is again. This is what. This is the estimated. Okay. This is not the actual model. This is the estimated model. This is why you cannot see error term, right? You can see there is hat here, and this is our beta 0, our coefficients for the constant. These are our coefficients for the slopes. How many independent variables we have in this example? We have 3, right? We have n, we have p, we have I. And again, we use I, see small I. That means this data is cross-section, right? Cross-section data. So in order to check whether we have heteroskedasticity in this model or not, okay, we will need to use the Prospegen test. One of the ways, okay? There's another way. We are going to see the white test later. The Prospegen test is one of the ways. In order to run the test for the Prospegen, we need to come up with the auxiliary equation. This is why we need to observe, we need to get the residuals from these early estimated models. We will subtract these estimated values of the models from the actual values of y, okay, and we square them, okay, and then we rewrite our equation for the model auxiliary equation in a way that we change the names of the parameters, okay. Instead of betas, we use alphas, alpha 1, alpha 2, alpha 3. How many degrees of freedom we have? Because we have 3 variables, right? 3 variables. We have 3 variables, then we have degrees of freedom equals to 3. Okay. How we calculate the test statistics? We multiply the number of observation times the number, the value of the R squared. Okay. So the chi-square statistics, test statistics will equals to 1.455. So with the degrees of freedom 3, 5% significance critical value, we need to go back to the table, okay, to the chi-square table, okay, the chi-square table where we can get the critical values, and then we do the comparison to see where is the rejection, whether we reject the null hypothesis or we do not reject the null hypothesis. Now, because the critical values is this much, and the test statistics value is this much, which is less than the critical value from the table, we cannot reject the null hypothesis. Okay, we cannot reject the null hypothesis, which actually says that alpha 1 equals to the alpha 2 that equals to 2, and there is no evidence. Okay, in this case, okay, in this example, there is no evidence of heteroskedasticity by using Prospegen test. Okay, by using the Prospegen test that show us that the model is free from heteroskedasticity problem. Going to the second way, how we actually test for the heteroskedasticity, that is white test. White test investigates whether the squared residuals can be explained by the equations dependent variables and the squares and the cross products. Later on, we will see how we build it. The only difference is how we makes our auxiliary equation. Okay, as the step, again, 3 steps. Step 1, we obtain the residuals. Okay, we obtain the residuals. After we obtain the residuals, because here we have 2 independent variables. Yes, this also what we call weaknesses from the white test. It will be harder if we have more explanatory variables. In case we have only 2, then our auxiliary equation will be specified as the original one, which is this one. Okay, and we will then plus we add 1 more coefficient that is for the square of each independent variable, x1 and x2. So x1 squared plus x2 squared plus the additional coefficient that is multiplied. Okay, the multiplication product. Okay, we multiply x1 and x2 from our original model plus the error term. So the difference between Prosh-Pagan and white test is the auxiliary equation here. And then the hypothesis that we are going to develop, instead of only 2, now we have more. We have, again, we use only the slope coefficients, not the, we don't include the constant coefficients, okay? The slope coefficients, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, because we have 5, 1, 2, 3, 4, 5, okay? That equals to 0. And yes, null hypothesis is false. That's for our alternative hypothesis. Similar test statistics we use. Degrees of freedom is again the slope coefficients, the number of slope coefficients in our model. In the Prosh-Pagan, we say that it's only 2, 1 and 2, right? Here we have 5. So the degrees of freedom will be higher, 5. And this, yeah, the weakness of the white is that with the number of explanatory variables in the original regression raises the number of this right-hand side, okay? Because if we have, this is only for 2 independent variables. Imagine if we have 5, okay? Imagine if we have 5 independent variables. We need to square each one, okay? Then we need to multiply and see the time product for each one times the others. So the number of slope coefficients will be even higher, okay? So yeah, the white test auxiliary goes up much faster. So if heteroskedasticity is found, maybe later we will have example on how we actually run the white test. How we can actually, but because we use the same example, then definitely the way that, let me see, I think we have one example of white test. No, I'm sorry. Oh, no. Oh, sorry, it's not there. Anyway, if we actually use the white test, of course, the white test will follow the same steps, okay? And if the example is there, maybe I could show. I'm really sorry, maybe I mistakenly removed from the slides, where actually we can see that the number of parameters, the number of coefficients for each explanatory variables are there, but because we have maybe higher number of independent variables, the alphas will be higher. But we will still follow the same procedure, the same test statistics, but the degrees of freedom will be different. Okay, the degrees of freedom will be different. And then once we get it from the critical values from the table, chi-square table, and from the test statistics, we compare, and then we see whether we reject or not reject the null hypothesis, and we proceed to draw for our conclusion whether the heteroskedasticity exists or not exists in the model. In case the heteroskedasticity exists in the model, that is not the end of the life. We have some, again, as we have remedies for the serial correlation, we also have some remedies for the heteroskedasticity. Okay, heteroskedasticity is found. In case we have heteroskedasticity, the first thing we to do is to examine the equation carefully for specification errors, because sometimes we run the remedies, but the problem is that we have misspecified our model in the first place. If we could ensure that our first model is correctly specified in terms of functional form, in terms of the number of independent variables, that we do not omit any important independent variables, then, and we still see that there is a problem of heteroskedasticity, that is where we apply, okay, heteroskedasticity remedies. So if there is no obvious specification errors, the heteroskedasticity is pure heteroskedasticity, okay, in nature. So one of the following remedies, the two remedies that I would like to introduce is heteroskedasticity corrected We call it HC, standard errors. Okay, and the other one is to redefine the variables or redefining the variables. If we could change and make sure that we use different proxy or different functional form, or take logarithm for the variables, or sometimes in such situation it might necessary to rethink project in terms of underlying theory, so we can use different variables, or we include variables that is from different theories. So redefining of the variables, like for example, I think I will end with this example. The total expenditure by the city governments. Okay, again, this cross section, we have population, we have expenditure, we have population, we have income, and we have average wages. And as I said, like for the case of Malaysia, if you go to different states, you can find that these variables are not the same. I mean, there is some gaps and there's some differences in terms of wages, in terms of income, in terms of population from one state to another. So definitely there is a sign that you can see that there is an early signs that shows that heteroskedasticity might appears in our model. So yes, instead of using maybe we can redefine. Okay, we can redefine our variables in order to get rid of the heteroskedasticity problem. And instead of taking population as one independent variables, maybe we can transform. Okay, or redefine the variables in terms of how much the expenditure per population, meaning how much the expenditure we divide expenditure by the population, or the income of the city. Okay, the income in the city by the population, and we can see this new variable that is we generated is going to change the results, and we ensure that heteroskedasticity problems is removed from the model. So yes, this is what we call slope with large cities. This slope with slope without large cities. This in different we call aggregate city expenditure function. We can see the difference between income and expenditure. Okay, the income and expenditure. How is the model that fit for small cities or large cities, or small states or large states? Yes, so redefining the variable could be one of the solution to finish, or to one of the remedies, okay, for the heteroskedasticity problems. Similarly, for the per capita, income per capita, and also expenditure per capita. Yes, I think I will stop here, as I guess the time is already past. I'm really sorry, because usually when I discuss this, for my classes, I discuss the serial correlation in one full class and heteroskedasticity in different class. But to put them together, to discuss them in the same time, yeah, takes longer time usually. But I hope that I could manage to explain it in a way that you could somehow understand it. And forgive me for any shortcoming, and I didn't have enough time to make any hands-on for the heteroskedasticity. Sorry, I will leave the rest of the task for the lecturers and Dr. Chua to help you with this, but you still can communicate with me anytime if you need help, if you have any questions or any things to ask or clarifications. I'm always ready to support and help with my capacity. Thank you so much for my sides. I appreciate your listening, and thank you so much. I appreciate it. Thank you. Assalamu alaikum.
Thank you, Dr. Osaid, for the comprehensive presentation. So we
Should
shall
I-
now proceed. Yes. So we shall now proceed to the second Q&A session. So
Yes, please.
if there are any questions, participants may either unmute and ask directly, or type their questions in the chat box. Thank you.
I think one is typing. Okay, let me just read. Aini Nurul Zakiya Abdul Rahman is asking, can a model suffer from both heteroskedasticity? Yes, there is a problem. This sometimes, especially, yes, if we use, this is why actually whenever we run any model, whether we use time series or cross section or even panel data, sometimes we also run panel data analysis, we still check the diagnostic checking. We call it diagnostic checking, whether we have problem of multicollinearity, heteroskedasticity, serial correlation, and from there we can detect all these problems using the one that I explained. And yeah, it's possible. How can we determine whether the heteroskedasticity is caused by the specification error? Again, we need to go back to the underpinning theory. Okay, the underpinning theory that explains the model that you are specifying. Of course, the models are different. Okay, the models are different whether you are using econometric modeling for macroeconomics, microeconomics, financial economics, energy economics, if you are using any kind of models, international trade, any models will actually have its own characteristics, and these models needs to be developed and specified based on the underpinning theories. If you are sure and you make sure that you are correctly specify the models, you follow you included the most important variables in your models, and you make sure that, or at least the proxy, okay, the proxy of any independent variables you include in your model, then you may say that, yes, I'm pretty sure that my model is correctly specified. Then, in this case, you still find the problem of serial correlation or heteroskedasticity. That is where you can mention and you can say that's pure, okay, pure serial correlation or pure heteroskedasticity. Okay, that's why before even we run any kind of analysis, we make sure that our econometric models is correctly specified. Okay, just to make sure that later on we will not have problem of heteroskedasticity or serial correlation in our models. Okay, I hope I answered the question. Is there any other question or anybody would like to ask? Feel free, please. Open your, unmute yourself. It's okay. I wish one day, inshallah, we can visit UiTM Kedah and we meet with all of you. And you are also most welcome to come to AIU, our campus, Al-Bukhari International University in Al-Wasita. Is a very good and very nice campus. That's also good. Maybe, inshallah, if we can have the opportunity, Dr. Chua, we can arrange for something and a visit. I hope that will be a very great experience. So there's no other question?
Hello. I
Yes,
have a question. I
Yeah,
am
go ahead.
Aina from KBA 2724C. So my question, what are the most commonly used method to correct the heteroskedasticity in regression analysis?
Okay. If you, of course, if you use time series, and we ensure that we have correctly specified our model and our regression analysis detect any problems, heteroskedasticity, and we ensure that there is pure heteroskedasticity or maybe pure serial correlation, we actually can say, yes, maybe the best tests is the one that we discuss, Proshpagan or white test for the heteroskedasticity, Durbin-Watson or Lagrange multiplier for the serial correlation. But yeah, there are others actually, because the econometricians and statisticians are always making research and coming up with new tests and also new ways to detect these kind of problems. But these are the most widely used, okay, the most widely used tests. Thank you. Back to you, Dr. Chua, please.
Okay, so if there are no further questions, we have now has come to the end of today's webinar. So on behalf of Department of Economics, University Technology Mara Cawangan Kedah and the organizing committee, I would like to express our sincere appreciation to our distinguished guest speaker, Dr. Said, for his valuable sharing and insightful presentation throughout today's session. We are truly grateful for his time, effort, and expertise in making this webinar meaningful and beneficial for all of the participants. We would also like to extend our appreciation to all lecturers and students for your present support and active participation throughout this program. Before we conclude, may I kindly invite all participants to switch on their cameras for a group photo session. Thank you.
All right, all the students, can you please on your camera, please? All right, we will take the picture now. 1, 2. All right, Dr. Siti here. Okay, 1, 2, 3. Okay, one more time. 1, 2, 3. Okay, good. Thank you, everyone.
Okay, with that, we officially conclude today's webinar. Thank you once again for your participation and cooperation. Assalamualaikum warahmatullahi wabarakatuh and have a pleasant day ahead. Thank you.
Waalaikumsalam.